Hello, this is Matt Dean with A Plus College Ready, and today we're going to work some problems dealing with work, power, and energy. Start off with question 1. You lift straight up a 4-kilogram box to a height of 2 meters above the ground. The box moves at a constant velocity for the entire displacement. How much work did you do on the box? Key point is this term constant velocity. That tells you that there's no net force acting on the object, which means you're lifting, so we'll call that your lift force, we'll call it an applied force. You're lifting with a force that's equal but opposite to the weight or the force of gravity. So there's no net force acting on the box. The work done by you is going to be equal to force times distance times the cosine of theta, where theta is the angle between the direction of the displacement and the direction of the force that's causing that work to happen. Well, in this case, the displacement's going to be straight up. You're lifting straight up, so the angle is 0. So we'll have work equals the force. The force here has to be the weight, not the mass. So you need to take 4 kilograms times 9.81 meters per second squared. You end up with a force of 39.2 newtons. Up. You're moving this box a distance of 2 meters. Also up. Times the cosine of 0. Cosine of 0 is 1. So you do the math. 39.2 times 2 times the cosine of 0. You end up with a work done of 78.4 joules. And it's positive, because the cosine of 0 is positive 1. The work you're doing is in the same direction of motion. Work is positive. Here's question 2. Very much similar problem. This time, though, you're asking for how much work did the gravitational force do. So you're doing work on the box. Gravity's also doing work on the box. We're going to calculate that work the same way. FD cosine theta. Again, we know there's no net force. So the force being applied to the box by the earth, in this case by gravity, is still 39.2 newtons. The box is still moving 2 meters. But this time the angle between the displacement and the force is 180 degrees. The cosine of 180 is negative 1. So therefore, when you do the math, 39.2 times 2 meters times the cosine of 180, you end up with a work done of negative 78.4 joules. Typically, when something is moving in the opposite direction of the displacement, or of the force rather, the work is going to be negative work. All right, here's question 3. You lift straight up again a 4-kilogram box to a height of 2 meters. The box moved at a constant velocity for the entire displacement. How much net work was done on the box? Well, since there's no net force, there can be no net work, because we could calculate net work this way. We could say the net work is equal to the net force times the distance times the cosine of theta. Well, the net force is 0. So therefore, the work done is 0. We know that because we also know that work is equal to change in kinetic energy. And in this case, since there's a constant velocity, the kinetic energy change is 0. Therefore, the net work done is 0. And I think I just got ahead of myself. It says you lift a 4-kilogram box to a height of 2 meters above the ground. The box moved at a constant velocity for the entire displacement. By how much did the speed of the box change during the displacement? Again, since there's no net force, there's no net work. And again, remember that net work equals change in kinetic energy. This is 0. Therefore, the change in kinetic energy is 0. And we know that kinetic energy is 1/2 mv squared. Well, the mass can't change. In this case, the velocity can't change either, because there's 0 change in kinetic energy. All right, now we get to something a little different. Problem number 5. In this case, we're pulling a trash can, across a flat surface. We've got a rope hooked up to it. We're pulling on that rope with 50 newtons of applied force to the right. There's some friction acting 30 newtons between the surface and the trash can. We pull it for 10 meters. We want to draw a free body diagram that depicts all of the forces. So let's do that down here. So we're applying a force of 50 newtons to the right. That's our FA, that's our applied force. We know that friction always acts in the opposite direction of motion. It's going to be our frictional force. We'll label that F. We know that this arrow for friction is going to be less than the applied force arrow. And we know that it needs to be shorter because the frictional force is only 30 newtons, whereas the applied force is 50 newtons. We have weight acting down. Since we're on a nice flat surface, that's going to be balanced out by an equal but opposite force. And we'll label that as Fn acting up, the normal force. So those are our 4 forces acting on the box. In this case, the 10 meters doesn't matter. It's not a force, it's a distance. So now let's move on to problem number 6. Here's problem 6. This time we want to know how much work is done by the applied force. Well, again, we go to work equals FD cosine theta. Well, the applied force is 50 newtons. It's moving the box 10 meters. And it's moving the box in the same direction as the force. Therefore, the angle between the force and the displacement is 0. So cosine of 0. Remember, the cosine of 0 is just 1. So when we multiply this out, the work comes out to be 500 Newton meters, or 500 joules, which is B. Problem 7, a very similar problem. This time we want to know how much work was done by the frictional force. Well, the frictional force is acting in the opposite direction of the motion. Again, we'll go to work equals FD cosine theta. The frictional force is 30 newtons. The distance is still 10 meters. But this time the angle between the displacement and the frictional force is 180 degrees in the opposite direction. Remember that the cosine of 180 degrees, or the cosine of 180, is negative 1. So when we do the math here, we end up with negative 300 Newton meters, or joules. So we're looking at answer C is the correct answer. Let's go to problem 8. And guys, I'm going to go back and revisit problem 8 for a second. I just completely misread the problem. I read this as how much net work was done by on the trash can. It's not what question 8 says. It asks how much work was done by the gravitational force. We're going to work that pretty much like we just did with the net force problem. So we're going to use work equals FD cosine theta. Remember, the force of gravity is going to be the weight of the object, which was 39.2 newtons. The distance moved, 10 meters. But the gravity force is acting at an angle of 270 degrees away from the angle of displacement. So this is going to be times the cosine of 270. And the cosine of 270 is 0. So we get 0 net work done by the gravitational force. And then again in question 9, we got next question, question 9, wants to know how much work was done by the normal force on the trash can. Well, normal force, remember, since we're on a flat surface, is going to be equal but opposite to the weight. So let's take the mass, 4 kilograms, multiply that by G, 9.81. get a weight of 39.24 newtons. Well, that weight, since we're on flat ground, is also going to be equal but opposite to the normal force. Well, if we calculate work, work equals force, 39.24 newtons, times distance, 10 meters. But in this case, the normal force is acting at 90 degrees above the displacement, above the direction of the displacement. So this is going to be times the cosine of 90. Well, the cosine of 90 is 0, which means the work done by the normal force, and also in this case the work done by gravity, both of those are equal to 0. Zero net work done by the normal force. Question 10 is the one that asks for the net work. And remember that net work, we could think of it as equal to net force times distance times cosine of theta. Or we could take the work done by the applied force, which was 500 newtons, minus the work done by frictional force in the opposite direction of 300 newtons, to end up, and I keep saying newtons, but joules, these should be joules, to end up with 200 joules. If we use this equation, the net force is 20 newtons. The distance is 10 meters. The angle between the displacement and the net force is 0. Calculate that out, and we still end up with 200 joules of net work done on this object. Here's question 11. If we assume the initial speed of the chem was 0, what is its speed after traveling 10 meters? The 10 meters described above. Well, you got to remember that the net work is equal to the change in kinetic energy. So we did 200 joules of net work, and that's got to equal to the change in kinetic energy. In this case, it's got to equal the final kinetic energy, since we started off with 0 kinetic energy. So 1/2 mv squared. Do a little work here. Go ahead and plug in the mass. The mass of our chem was 4 kilograms. All right, if we solve that out for V, go ahead and do the algebra, solve for V. V comes out to be 10 meters per second. So in this case, the work we did caused an increase in speed, which in turn caused an increase in the kinetic energy of the chem. All right, here's question 12. So in this case, we have a bike rider. He and his bike have a combined mass of 90 kilograms. The rider starts from rest and rolls down an inclined plane 500 meters long. So we're saying the length of this leg is 500 meters. The angle of incline, this angle right in here, is 5 degrees. And we have a frictional force acting at 60 newtons. And we want to find the speed of the biker at the bottom of the hill. We also know the combined mass of the biker and the bike, 90 kilograms. All right, there's several ways we could do this problem, but let's stick with an energy approach here. Let's first of all draw this hill out as if it were a triangle, and let's use the fact that the hypotenuse of this triangle is 500 and this angle is 5, and let's calculate the height. So we're going to use the sine function, and we're going to say that the sine of 5 degrees is equal to the opposite side, which we'll just call y in this case, over the hypotenuse of 500. So if we solve that out, sine of 5 times 500, we get a height of about 43.6 meters. Now we can use that height, 43.6 meters, to calculate the amount of gravitational potential energy that the biker and the bike have at the top of the hill. Remember, we use that mgh, some people write mg delta y. So to calculate the gravitational potential energy, let's take the mass, 90 kilograms, times g, times the height, which in this case is 43.6 meters. If we multiply that out, that ends up giving us an initial amount of a gravitational potential energy of 38,494 joules. So that's how much potential energy the biker and the bike have at the top of the hill. Well, if there weren't any friction, as the bike rolled down the hill, at the bottom of the hill, all of that potential energy would become kinetic. So the change in potential would equal the change in kinetic. But in this case, there's friction. Friction is doing negative work, which means it's canceling out some of that gravitational potential energy. So let's calculate the amount of work done by the frictional force. So what we know is that we know work equals FD cosine theta. The frictional force was 60 newtons. The bike is moving a distance of 500 meters down the incline. And in this case, the angle between the displacement and the direction of the frictional force, they're in completely opposite directions. So that's 180 degrees. We do the math here. We end up with a work of 30,000, negative 30,000 newtons. So this negative 30,000 newtons cancels out 30,000 of our original potential energy, which leaves us with only 8,494 joules of energy that become kinetic. So by the time he gets to the bottom of the hill, the rider has an amount of kinetic energy equal to 8,494 joules. We can set that equal to 1/2 mv squared. Plug in 90 for the mass. And then solve that out for v. And when we do get that solved out for v, we get a velocity of 13.7 meters per second. So again, the rider's potential energy, part of it was canceled out by the negative work done by friction. Some of that energy was turned to heat. What was left was 8,494 joules of energy that were converted to kinetic energy. We set that equal to 1/2 mv squared, solve for v, get 13.7 meters per second. All right, here's problem 13. A box slides down a frictionless inclined plane of length 10 meters. The plane is inclined at an angle of 20 degrees above the ground. If the box starts from rest, what is its speed at the bottom of the inclined plane? It's a very similar problem to the last one. So our inclined plane is length 10 meters. Our angle of incline is 20 degrees. We're not given a mass here, and that throws a lot of people off. But since there's no friction, we can say that the amount of gravitational potential energy that we start off with at the top of the plane is equal to the kinetic energy at the bottom of the plane. Well, we know that gravitational potential energy is equal to mg delta y, or mgh, and we know that the kinetic energy is 1/2 mv squared. As I hope you can see, the masses cancel out here. We don't need to know the mass. We're trying to find the speed at the bottom of the hill, so let's take this equation right here. Let's solve that for v. So we're going to need to multiply both sides by 2 to get rid of that 1/2. So that's going to give us 2g delta y is equal to v squared. We're going to take the square root of both sides. So our speed is equal to the square root of 2g delta y. Well, we know what g is, 9.81. We know what delta y is. Actually, we need to find delta y because delta y is going to be the height. So to find that height, we need to use the sine function. And we're going to say the sine of 20, we'll call this y, equals opposite of y over the hypotenuse of 10. So that gives us a height of 3.42 meters. So then we plug into our equation up top here. So we're going to say that speed equals the square root of 2 times g times delta y, which is 3.42. Take the square root of that whole quantity, and we end up with a speed of 8.19 meters per second at the bottom of the hill. In this case, since there was no friction, all of the gravitational potential energy at the top of the plane was converted to kinetic energy by the time the box reached the bottom of the plane. All right, so now let's take a look at the long free response question. We have a wheel rolling down an inclined plane at angle theta above the ground. First thing we want to know is, or we want to do, is indicate all the forces that act on this wheel. Essentially drawing almost like a free body diagram, but we want to show the forces at the points at which they act. So the first thing we're going to do is to draw in weight. We usually draw weight from the center of mass, and weight acts straight down. We're going to label this as mg. We could also draw in a normal force. Remember, a normal force acts at 90-degree angles to the surface, and it's acting from the surface. So maybe something like that. We'll label that as N. And then the third and final force that we need to put in is the frictional force. Friction acts from the point of contact of the wheel and the plane, and it acts in the opposite direction of the motion. So maybe like so. So those are the only actual forces acting on the wheel. We don't show components. Second part wants to know which force causes a change in the angular velocity, so the speed at which it rotates. And the short answer to that is that the only force here that's causing a torque, causing a turn of the wheel, is the frictional force. So the answer to 2, frictional force, is causing the torque. It's causing the wheel to change its rotation. All right, so part B. For this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static friction force. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force, or force component, directed opposite to the force of friction. Derive an expression for the linear acceleration of the wheel center of mass in terms of m, theta, and physical constants as appropriate. Well, here's what we know. We know we've got this plane. Think of our wheel on the plane. We have a weight acting down. So let's draw this in as our weight. We're going to take that weight and break it into components. And we're going to do vector resolution on it. And we're going to break it into a component that we're going to call F parallel. And we'll call this component over here F perpendicular. This angle right here turns out to be the same as this angle right here, because we have similar triangles. This angle is theta, therefore this angle right here also theta. The part of the weight that's making the wheel go down the hill is the parallel component of that weight. And we could find that using sine. So we could say the sine theta is equal to F parallel. Well, in this case, our hypotenuse is our weight. So F parallel over mg, which means that F parallel is equal to mg sine theta. So let's think about the acceleration down this plane. To find the acceleration, we need to know the net force. So we could say that the net force, write it this way, acting down the plane is going to be equal to the parallel component of the weight, mg sine theta, minus the frictional force. So let's rewrite that a little bit different way down here. Because what they tell us is that the frictional force is 0.4 of the force acting opposite of friction. Well, that's this force, which means the frictional force is 0.4 times mg sine theta. All right, so we could do a little work on that. We could simplify this, and that means that the net force is equal to 0.6 mg sine theta. Well, that's the net force. We know that acceleration is equal to the net force, 0.6 mg sine theta, over the mass. So we could cancel out the masses. So our acceleration is 0.6 times g over sine theta. And that's your answer to part B. Finally, part C wants to know that if we started on an incline, we had a wheel on an incline, and then later on the same ramp, we had a block of ice. If these two objects, the wheel and the block of ice, started at the same height, we want to know which one reaches the bottom of the ramp with the greatest speed. There's a couple different ways you could answer this. One of them is that ice. We've got ice here. Ice is very slick, which means there's very little friction. So we could say the block of ice is going to make it to the bottom first because there's very little friction acting between it and the plane. Whereas the wheel, there's a little bit more friction. So because there's more net force acting on the block of ice, it will accelerate faster and therefore have a greater speed once it reaches the bottom of the plane. The other way to explain it is in terms of energy, and that's what part 2 wants us to look at. All right, let's make even a bad assumption here. Let's say there was no friction here or here. For the wheel, the gravitational potential energy that we started with at the top is eventually going to get converted to kinetic energy by the time it reaches the bottom. Some of that kinetic energy is going to be translational, linear. But that wheel is also going to spin. I'm going to use KT to mean translational kinetic energy. But because it's spinning, some of that kinetic energy is also rotational kinetic energy. Whereas with the block of ice, all the gravitational potential energy is going to be translational, straight line kinetic energy. Which means, with the wheel, some of the energy is going to go into making it move. Which means it's going to be moving slower than the block of ice. The block of ice, no matter which way you look at it, one or two, will make it to the bottom with a faster speed than the wheel. Hope that helps.